Hello, everybody, and welcome to the Solving Stuff with SOSA, Electricity, and Magnetism videos. We are in learning module number 1 that has to do with electrostatics. And we are discussing situations that have to do with continuous charges and objects with a defined geometry. In the previous 2 videos, we analyzed a charged line and a charged ring and the electrical field that these generated at a certain point, at a certain distance from these charged objects. In this video, we are going to analyze a charged disk. And so the situation we have is that we have a disk that has a certain radius defined by r, and we want to find or understand or analyze what the electrical field would be generated from this disk at a certain distance z from the center of the disk. And this is with regards to a point that we're going to call P. Now, there's an important difference here with regards to the previous analysis we did. In the previous analysis, the distribution of the charge was along a linear surface. So we had a constant called lambda, which was the charge by unit of distance or length. In this situation, the charge isn't distributed linearly, it's distributed along a surface. So now we are going to have another constant that's called the area charge distance that we're going to represent as sigma. And what does sigma represent? Well, sigma is going to represent the total charge divided by the total superficial area. And that's going to be an important value that we're going to be working with. Now, the way we're going to do the analysis of this situation is that we're going to use the same procedure we did in the previous one. We're going to take a small portion or a small point that we're going to consider a point charge that has a charge dq. This charge is going to be at a certain direct distance from the point P that's going to be called R, forming a triangle, and it's going to be at a distance X from the center. The small distance that's generated here would be the differential of X, and so which is the accumulated X while we go along the ring towards R. And we're going to be analyzing the situation as if it were a point charge and then do some integration to add up all of the effects. So let's get to it. So let's analyze this. Again, the situation is very similar to what we had done previously. So if we place ourselves here in point P, we are going to have the following. We are going to have a electrical field. Use another color there. I'm going to use a let's see. I'm going to use blue. We're going to have an electrical field here. I'm going to use an orange. We're going to have an electrical field here that's being generated by this very small point here that we're going to be considering a point charge. And that electrical field that's being generated, we're going to call it dE dQ. And that electrical field is going to be at an angle that we're going to be calling alpha. This point that we're analyzing is at a distance X from the center, and it's at a height Z, and we have a distance R. That creates a triangle here. I'm going to do it here on the bottom. It creates a triangle where we have z and x, and we have r that's equal to the square root of x squared plus z squared. And the angle that we have here in this triangle, we're going to be calling alpha for now. Now, in the previous analysis we did, we noticed that in the end, what we want to find is the total electrical field that's being generated by this point, and we're going to be putting it here. I'm going to be saying this one is going upwards, and this is going to be our electrical field E. That's one we're looking for. Now, how do we find our electrical field E? Well, we know that this electrical field that's generated by the point is going to have two components. It's going to have an X component and it's going to have a Y component. However, we had already seen in the previous analysis that because of symmetry, if I grab another point charge that's at the same distance but on the opposing side, I'm also going to be generating a distance r, and I'm also going to be generating an electrical field dE dQ2, and that is also going to have an X component and a Y component. And what we had analyzed previously is that the X components are going to cancel each other out, and the Y components are going to add up. And so in the end, what we're going to be interested in is the adding up of these Y components. So what we're going to have is that we are going to have an electrical field up here that I'm going to be calling dE, which is that Y component of our electrical field dE dQ. And so the total electrical field generated by that point is going to be the integral of dE. Now dE is going to be dE dQ. That's going to be the Y component, which would be multiplied by the sine of alpha. Now, if we come back over here, we can find that the sine of alpha is equal to the opposing side, which is z, divided by r. Now, we also know that dE dQ is going to be K, which is the electrical constant, multiplied by the differential charge divided by r squared. And this would be multiplied by z divided by r. And so this is going to give us the integral of k z dq divided by r to the 3. Now, on the previous slide, we mentioned that there is a value that we're going to be calling sigma, which is the area, the density of charge, which is the charge per unit area, okay, which would basically be the charge, or the differential of the charge in this case, by the differential of the area. Or let's do it this way to understand it better. It's going to be the charge divided by the area. Now, in this case, the area for the differential, if we're going from 0, if we're located at a distance x, then the area is going to be pi multiplied by x squared. This gives us the following. It gives us that Q is equal to sigma pi times x squared. Now, in the end, we want dq. That's what we want over here. So we're going to apply a derivative here. So dq is going to be equal to sigma and pi are constants. We're going to do the derivative of 2x, which would be 2 I'm going to reorganize these. So it's going to be 2 pi sigma times x dx. And we can substitute that over here. And what we're going to have is that E is going to be equal to the integral of k z multiplied by 2 pi sigma x dx divided by r to the 3. Now, we know that r to the 3 is, r, we know that r is the square root of x squared plus z squared. So what we're going to have here in the denominator is that r to the 3 is going to be x squared times z squared elevated to the 3 halves. You got to be careful with that because I always write 2/3. It's 3 halves. And over here, we're just going to organize these things. So I'm going to say 2 pi k sigma z x dx. And there's a bunch of things there that are constants that we can bring out of the integral. So this is going to be E equals, we can bring out the 2, the pi, the k, the sigma, the z is constant as well. And we're going to be left with the integral of x dx divided by x squared plus z squared to the 3 divided by 2. And this integral would have or is going to have an interval. And that interval, in this case, x is going to go from 0 to r, which is the radius. And now what we have to do is that we have to solve this integral. That's the next, I'm sorry for my cough. That's the next step or challenge we have. So I'm going to erase some stuff here so we can go through that procedure. Bear with me here. I'm going to erase. Sorry about that. I'm gonna write the integral up here. So what we're looking for is E equals 2 pi k sigma z, the integral from 0 to r of x dx divided by x squared plus z squared to the 3 halves. That's what we are going to be looking for. And for that, if we remember the previous examples, we're going to be having to do some trigonometric manipulations here to find that. And to do that, I'm going to go back here to the triangle we had, and I'm going to change the name just for the purpose of the analysis. I'm going to change the name of this angle, and I'm going to call it theta. I'm going to call it theta, and we're going to be doing some manipulations there with our some trigonometric substitutions to be able to do this integral. Okay, so I'm going to be doing the following to solve this integral, and this is because I thought about this procedure. I've seen this procedure done in other videos, but I thought it was kind of fun to do it this way. Fun, doing integrals is fun, right? I thought it'd be fun to do it this way. First off, the first thing I'm going to do is I'm going to do a separation of this integral over here, and I'm going to do this. So I'm going to say that E is going to be equal to 2 pi k sigma. And I'm going to bring the z inside the integral. I'm going to leave the intervals aside for now. We're going to bring them back when we solve the. I'm going to bring the z inside, which is going to be x z dx divided by x squared plus z squared to the 3/2. And then I'm going to do the following. I'm going to separate this integral into 3 parts. Well, separate the factor that's inside there into 3 parts. I'm going to say E equals 2 pi k sigma. These are all constants. And I'm going to do the following. I'm going to do 3 fractions here. 1, 2, and 3. And what I'm going to do there is the following. Notice that the x squared plus z squared is elevated to the 3/2. This is actually the same as having the following. 2 pi k sigma. Sorry about my cough. xz dx. The denominator is exactly the same as having the square root of x squared plus z squared elevated to the 3. Okay. It's exactly the same thing. And so that means that what I'm going to do here is totally valid. I'm going to say that I'm going to separate this into 3 factors, x squared plus z squared, square root, x squared plus z squared, square root, and x squared plus z squared, square root. So the denominator, if I multiply these 3, I get it to the cube, which is something that's that I want. And then let's go with the denominator. I've got x and z, but I've got 3 things here. So I'm going to do with the numerator. I'm sorry. I'm going to go here with the numerator. I've got x and z, and what I'm going to do is the following. So I'm going to say that this is 1, this is x, and this is z. And I've got everything multiplied by dx. So notice that I've got 3 factors there. That's totally valid. I'm only separating these. And now let's look at the following. Well, first of all, let's look at the trigonometric expressions that we can do over here. So first off, I'm going to say that the tangent of theta is equal to z divided by x. Okay, that's just looking at the triangle and relating these there. And from this, what I can do as well is that I can say that x is equal to z divided by tangent, which is the same as saying x is z multiplied by cotangent. If I calculate the derivative of x, the derivative of x, which would be the derivative of z cotangent theta, the derivative, I'm sorry, I said x there. I made a mistake. Give me a moment. Boom, 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 boom. I want to mix things up here. Theta, it's theta. Theta. It's going to be z multiplied by cotangent of theta. Sorry about that. So if I calculate the differential of x, it is going to be the differential of cotangent, or the derivative of cotangent. The derivative of cotangent is minus cosecant squared. So I'm going to have minus z cosecant squared of theta d theta. And the other thing I can do is that I can elevate that to the square. I've got x squared is equal to z squared cotangent squared of theta. So I'm just going to mark these because I'm going to be needing them, or I'm going to be using this and this. Next up, I can also identify that, sorry about my cough again. I can identify that the sine of theta is going to be equal to z divided by the square root of x squared plus z squared. And I can also identify that the cosine of theta is equal to x divided by the square root of x squared plus z squared. And notice that I'm gonna write these down the other way around. I'm just gonna flip them. So the cosine of theta is x, and the sine divided by the square root of x squared plus z squared, and the sine of theta is z divided by x squared z squared. So notice what's happening here. Notice that this fellow over here is exactly the same as this one, and this fellow over here is exactly the same as this one. And I've already got dx over here, which I can substitute here. And I've got this expression here that I can substitute here. And so let's do that, and let's see what we get. So I'm going to erase the top part here. I'm going to erase this. And let's do these three substitutions and see what we get. So I'm going to have E equals 2 pi k sigma, that's a constant, times the integral of, okay, first off, I'm going to substitute the x squared here in this expression, and I'm going to get the following. I'm going to get 1 divided by the square root of z squared cotangent squared of theta plus z squared. Sorry about that again. This would be this. Next up, x divided by the square root of x squared plus z squared is cosine of theta. So this is going to be multiplied by cosine of theta. And so this is this. Next up, we've got z divided by x squared plus z squared. We just saw that this is sine of theta. So this here is this. And last but not least, we've got dx, which is minus z cosecant squared of theta d theta, which is basically this here. So we've got that. And let's see how we can now do some manipulations there to reduce that and be able to do the integral. Okay, I'm going to erase these lines here. And let's work on this here. So what we're going to have here, I'm going to zoom in on this part here. what we're going to have there is that in the end, we're going to have z, we're going to have the square root of z squared cotangent squared of theta plus z squared. This is the same as having, we can factor z squared, and we're going to have the cotangent squared of theta plus 1. And cotangent squared plus 1 is a trigonometric identity, which is cosecant squared. So this is going to be equal to c squared times cosecant squared of theta. And what's going to happen there is that the squares are going to be eliminated by the square root. And in the end, this is going to be equal to z times cosecant of theta. So having said that, we can substitute all of this for z cosecant of theta. We can do that. Okay. And so what are we going to oh, I'm sorry. Wait. Oh, I made a mistake there. That's in the denominator. Sorry about that. It would be 1 divided by z cosecant of theta, because that would be in the denominator. So once we have that, let's start seeing what we can eliminate here, or start to reduce to be able to solve the integral. Well, first, this z here goes away with this z over here. The cosecant here in the denominator goes away with this square. And what we are going to be left with is e equals 2 pi k sigma times the integral of cosine of theta times sine of theta, minus, there's a minus there, times cosecant of theta d theta. And we know that cosecant is equal to 1 divided by sine. So if we substitute, I'm going to erase this part here on the bottom just to continue with solving the integral. Have a little bit more space here. And so we're going to have that E equals 2 pi k sigma times the integral of minus cosine of theta multiplied by sine of theta multiplied by 1 divided by sine of theta d theta. So what's going to happen there? The signs are going to be eliminated, and I am going to be left with 2 pi k sigma times the integral of minus cosine of theta d theta. Okay. And so the integral of cosine is going to be sine. So in the end, the solution to this integral is going to be E equals 2 pi k sigma. Actually, there's a minus there, so let's put the minus outside. It's going to be minus 2 pi k sigma. The integral of cosine is going to be sine of theta. And if we go back to our erase that. If we go back to our trigonometric functions, then this is going to be equal to minus. I erased it again. It's going to be equal to minus 2 pi k sigma. And the sign of theta, we know that it's this fellow that we have here. So this is going to be multiplied by z divided by the square root of x squared plus z squared. And what we can do now is that we can bring back the intervals, the integration intervals that we were talking about, and those integration intervals went from 0 to r. And so let's substitute those. I'm going to erase this part here on the bottom. Just have a little bit more space. And what we're going to have is the following. Substituting the two intervals, we're going to have that E is equal to minus 2 pi k sigma. Substituting the first interval, we're going to have z divided by the square root of x squared plus r squared. And if we substitute the 0, what we're going to get is minus what is that? Minus z divided by the square root of 0. Oh, I made a mistake over here on this side. Sorry about that. This would be r squared times z squared. Sorry about that. This would be 0 squared plus z squared. And if you notice what's going to happen here, 0 squared plus z squared, square root of that is going to be z. So this z is going to eliminate with this z, and all of this is going to be equal to 1. And so organizing stuff here, it's going to be -1, but if we multiply everything by this negative value over here, in the end, what we're going to get is the expression that we were looking for. Oops, sorry about that again, which is 2 pi k sigma multiplied by 1 minus z divided by the square root of r squared plus z squared. And this would be the expression that represents the electrical field of a charged disk at a certain distance, z from the center.